Let me give you information about how are different series of spectral lines formed in hydrogen atomic spectrum. Okay. Now, the first series is Lyman. You know, Lyman series is formed when electrons get de-excited from any higher energy level to first orbit. So, in case of Lyman, the lower energy level is N1 and the higher energy level can be anything greater than 1, isn't it? So from any higher energy level, if the electron gets de-excited to first orbit, you know, the spectral line, whatever is formed, belongs to Lyman series. And you know, the region in which Lyman series or the spectral lines in Lyman series are observed is the UV region, right? Coming to Balmer series, N1 is 2, N2 is greater than 2. What does that indicate? From any higher energy level, if the electron gets de-excited to second orbit, the spectral lines, whatever are formed, belong to Balmer series. Now, this Balmer series is the one which we can see in visible region of electromagnetic radiation. Then there is a Paschen series, for which the lower energy level is 3 and higher energy levels are greater than 3. That means from any higher energy level, when electrons get de-excited to third orbit, the spectral lines are found in Paschen series, which of course is found in a near IR region, near infrared region. That means infrared region nearer to visible region. We know that the order goes this way: UV, then you have a visible, then you have IR, right? Of course, you have cosmic, you have gamma, you have X-rays, then UV, visible and IR, then of course microwaves, TV waves, and radio. This is the order, right? Already given this order. Now, coming to bracket series. From any higher energy level to fourth orbit, when electrons get de-excited, we get spectral lines in bracket series, and this series is observed in middle IR. Then there is a Fund series. Here the lower energy level is 5 and the higher energy level can be anything greater than 5. And now this you can say far IR. Far IR in the sense which is far away from visible with respect to visibility. Then finally we have something called Humphrey series. This one. So from any higher energy level to sixth orbit, whenever electrons get de-excited, You get spectral lines in Humphrey series. Even Humphrey series is observed in far IR region. Same thing. So these are different series observed in different region. Lyman, wherein the electrons get de-excited to first orbit. Balmer, second orbit. Paschen, third orbit. Brackett, fourth orbit. Pund, fifth orbit. Humphrey, sixth orbit. Okay. Let me give you some more clarity on this. Let us consider diagrammatic thing. Let this be the first orbit. Second, third, fourth, fifth, sixth. Let me take one more. Hope you can see, you can observe that there is a greater distance between the first and second orbit. But as we go away from the nucleus, I mean from second to third, or from third to fourth, or from fourth to fifth, like that, as we go on, distance between the adjacent levels is decreasing. Okay, so check this out. As we go away from the nucleus, distance between adjacent levels goes on decrease. Okay, you can see that properly. Now coming to the formation of spectral light, I told you that from any higher energy level, let me do this way. From any higher energy level, if the electron gets de-excited to first orbit, then the spectral line, whatever is formed, belongs to Lyman series, not just from 7. Consider from 6. Okay. 6th to 1st. Even 5th to 1st is okay. Then 4th to 1st. Let us take from 3rd to 1st. Even 2nd to 1st. Okay. So this way, when electrons get de-excited from any higher orbit to first orbit, it may be even from infinite orbit also. In such a case, you know, the series formed is called Lyman, and it is observed in UV region. Now let us check the other series. The second one, say Balmer. from any higher energy level to Balmer series. I mean, second orbit. Next, 6 to 2 second. This way. From third to second. That's it. From any higher energy level to second orbit. You get Balmer series, invisible region. Got it? Then from any higher energy level, say to the third orbit. Come on. And of course, from the fourth one. Okay. Look at the way I'm showing them. From any higher to third orbit. Okay, let me just tell you this. You know, when electronic de-excitation occurs from any higher energy level to third orbit, you get Paschen series in a near IR region. Come on. From any higher energy level to, let us go for the fourth orbit. Then this one. So this is when you get bracket series in middle IR region. Okay. Then from any higher energy level to the fifth orbit. Right. This is when you get fund series. Fund series in, of course, the far IR region. Don't say P fund, it's fund series. Finally, from any higher energy level to the sixth one. Of course, we can take any number of orbits, no problem. But here we get Humphrey series again in the far IR region. So check this out. You know what? This doesn't occur as such. I mean, the way we have discussed, it actually occurs this way. Suppose, see, yesterday I told you that suppose you are, say, at the seventh level, you may straight away get down to the first level, during which only one line is formed, I told you. Because you have come down, you have got de-excited in just one step or directly. So just one line is formed. Or else it may be like this also. See, from seventh, the electron may get de-excited to sixth. Then you get a line in Humphrey. From sixth, look at this, sixth to fifth, you get a line in fund. Now the one that has come to fifth may go down to fourth. You get a line in bracket. From fourth, it may go down to third orbit. get de-excited to third orbit. Then you get a line in Paschen series. Then from third to the second orbit, you get a line in Balmer. Or, I mean, after that, from second to first, you get a line in Lyman series. So this is how it may occur in steps also. See, you got lines in all the series, right? It may not be just this. It may be from 7th to 6th. From 6th, suppose in 6th you got this, this, and this. From 6th, it may just go down straightly to third one. Then you get a line in Humphrey first, then in Paschen. From third, come here. From third, it may go down to first. Then you get a line in Lyman series. Only 3 lines are formed, right? Suppose there is an electron in 7th orbit. It has straight away come down to third orbit. So you get a line in Paschen. From third, it may straight away go down to first orbit. You get a line in Lyman, only 2 lines. So this way there are several possibilities for the excited electron to get de-excited. So that is how, you get number of spectral lines, which in fact are grouped into different series depending on the region of the electromagnetic spectrum where they are formed. Okay. So this is a diagrammatical representation of the hydrogen atomic spectrum. Now let me give you one more interesting point. This is the most important one. The lower energy level is fixed. Let me recall your memory again. Coming to the lower energy level for different series. I've just given, but still, I mean the N1, if you consider for Lyman, the lower energy level is 1. Fixed. For Balmer it is 2nd. For Paschen it is 3rd. For Brackett it is 4th. For Fund it is 5th. For Humphrey it is 6th. Right? These are fixed. But the thing is, what is N2? Now for N2, you need to have some specific information of what the line is. The first line in any series is called H alpha line. Okay. If you want N2 for the first line, you just add 1 to your N1 value. For example, if you want the N2 value for first line in Lyman series, what is that? N1 for Lyman series is fixed. That is 1. So to that 1, you just add 1. That means N2 for the first line is a 2 in case of Lyman series. Now go for the second line. I'll give you so many examples. Don't worry. H beta line. This is N1 plus 2. Just add 2 if you want for the second line. And that is called H beta line. Coming to the third line, H gamma line. N1 plus 3. Go for the fourth line. It is called H delta line, alpha, beta, gamma, delta. N1 plus 4, that is the fourth line. And you know the last line in any series is of course called series limit, or you can also say limiting the line of the series. For that, N2 is infinite. Got it? Now let me just give you one or two examples here itself. Suppose if you want the N1 and N2 values, because only when you know the values of N1 and N2, you can calculate the wave number, wavelength, frequency, and energy of any spectral line. That is what for we are discussing all this information. Now let me say, let me just take one or two examples here. Of course, we'll give you more. Suppose you want for the fourth line in say Balmer series. For this line, see, whenever I say Balmer, I told you that N1 is fixed. What is N1? Yes, it is fixed. N1 is 2. Right? Because it is Balmer, N1 is 2. And now they are asking for the fourth line. For fourth line, nothing but a H delta line. You just add 4 to your N1. Okay. So N2 will be 2 plus 4. If it is for fourth line, you just add 4. Okay. Next. Suppose let us take one more. Supposing if you want for the third line in fund series, what are the N1 and N2 values? See, when I say fund series, remember N1 is equal to, yes, of course, for fund N1 is fixed. It is very clear. You can see that. For fund N1 is 5. And when they are asking for the third line, for H gamma line, you just add a 3 to your N1. Okay. So that is about the N1 and N2 values. Only when you can write the N1 and N2 values, you'll be able to solve the question. Let me give you some more for clarity's sake. We'll then go for the expression. Supposing if you want for the second line or say H beta line in bracket series, hope you can say, because it is bracket, N1 is 4, fixed, right? And because they are asking for the second line, just add a 2 to get the value of N2. I think this is clear, right? Now coming to one more. Supposing it, you want for the fourth line in Lyman series. What is the fourth line? H delta line in Lyman series. For Lyman, you all know that the value of N1 is just 1, right? Because it is the lower energy level in case of Lyman series. Now they are asking for the fourth line. So just add 4 to your N1. Just a second. Adding 4 will give us 5. So N1 is 1 and N2 is 5. Right? One last example. Supposing if there is a series limit, I mean, the last line, say in a Paschen series, what are the N1 and N2 values for that? Say because it is Paschen, N1 is 3. And because they have asked for series limit, without any hesitation, you can just say N2 is infinite. Got it? That's it. So this is how, if you can write the N1 and N2 values, solving problems is just easy. Let me give you the expressions one by one before going for the problem. Important formulae. Come on. You can just go for the expression. Suppose you want the wave number of the spectral line formed in Balmer series. Okay, then you can, of course, go for RH into, yes, of course, Z square, where Z is atomic number, into 1 by 2 square minus 1 by n square, where the value of n is greater than 2. This was actually given by Balmer, and this is called Balmer's equation. Now this Balmer's equation can be used only for spectral lines formed in Balmer series. Now this was later modified by Rydberg, and he gave this equation called Rydberg-Ridge equation. Now this equation can of course be used in case of any line in any series. Any line in any series. Okay, of course, the same thing is being modified. Check out this. See, this is the lower energy level, right? In case of Balmer, so that can be given as N1. And this is anyway greater than 2. For Balmer, of course, N2 is anyway greater than 2. So this is N1 and this is N2. This is what is being used by Rydberg in giving his expression. Nu bar is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. Where of course the N1 and N2 are known things. N1 is the lower energy level. N2 is the higher energy level. Z is of course the atomic number. And this is very interesting. Let me tell you that RH is called Rydberg's constant. But this is only for hydrogen. That is the reason why we have written it RH. And if you want for other species, you can take RH into Z square. So let me give you some clarity on that. The value of RH can be written as 109,677.8 per centimeter. Or if you want this, in per meter, you just multiply this by 100 to convert that into per meter. So 109,677.8 per centimeter or 109,677.8 into 100 per meter. So for any hydrogen-like species, this is only for hydrogen, yes? Then for any hydrogen-like species, what do you mean by hydrogen-like species? Means those with one electron in them. For example, take helium plus. Helium as such contains 2 electrons, but there is a positive charge, means it has lost 1 electron. So this is 2 minus 1. You can also take Li plus 2. This can be given as 3 minus 2. You can also take Be plus 3. This is 4 minus 3. Now these are called hydrogen-like species. See, for hydrogen-like species, you just take RH as it is multiplied by Z square. Okay, so this is for hydrogen. Then the second one is for hydrogen-like species. Hope this is clear. So this is the expression for wave number. Let me give you expressions for wavelength, frequency, even energy of the spectral lines. Of course, these are all related. Let me go for the next step. You know this nu bar can be written as RH into Z square into, you know, the LCM can be given as N1 square into N2 square. Then this will be like N2 square minus N1 square. Isn't 1 by N1 square minus 1 by N2 square is written in this format. Hope this is clear. Now, let us go for the expression for lambda. We know that nu bar is equal to 1 by lambda. So lambda can be written as 1 by nu bar. Then let me go for 1 by, come on, take that nu bar thing, 1 by RH into Z square into N1 square into N2 square. See, this has come into numerator by N2 square minus N1 square. Got it? So this is the expression for calculating the wavelength of the spectral lines. Now, let me give you one very interesting information. Let us consider this 1 by RH. You know, 1 by RH can be written as 1 by 109,677.8 per centimeter. You know, this comes out to be 912 into 10 power minus 8 centimeters. Or let me write this as 912 angstrom, because we know that 10 power minus 8 centimeters is nothing but 1 angstrom. Now, this is what you got. Let me give you a simplified formula for calculating the wavelength of the spectral line. Come on, lambda can be written as 912 into N1 square into N2 square by N2 square minus N1 square into 1 by Z square angstroms. We have taken this 1 by Z square here. Check this out. And this also is an important relation. You can solve any number of questions. You got expression for nu bar, you got expression for lambda. Right? Then, of course, the other. Now, going for the expression for, say, frequency. We know that a nu bar is equal to nu by c. Hope you remember. Therefore, nu can be written as c nu bar, isn't it? Nu is equal to c nu bar. Now we know what nu bar is. I've already written right at the beginning. C into, come on, nu bar is RH into Z square into, of course, 1 by N1 square minus 1 by N2 square. Right? So therefore, nu is equal to, let me write the final expression. C RH into Z square. Then this one is, of course, N1 square into N2 square. And in the numerator, it will be N2 square minus N1. So this is the expression for calculating the frequency of spectral light. Let me also write the expression for energy of the spectral lines. Come on. Again, we know that E is equal to HC nu bar. Hope you all remember. Yes, I am going to write the final expression. Energy is equal to HC into what is nu bar? Nu bar is RH into Z square into, of course, 1 by N1 square minus 1 by N2 square. If you want, you can write one more step. A is equal to HC into RH into Z square into N2 square minus N1 square by N1 square into N2 square. So that is a final expression for calculating energy of the spectral light. So you got all different relations: wave number, wavelength, frequency, and energy. Of course, all are interrelated. If you can just write the expression for wave number, you can go for all the other. Right? Let me also give you 3 more relations for the calculation of number of spectral light. Okay. Now within this, I have 3 cases. From any higher energy level to ground state. In such a case, you know, the expression for calculating the number of spectral lines can be given as n into n minus 1 by 2, where n is a higher energy level. Let me give you an example for this. For example, from 5th orbit to 1st orbit, I mean 5th orbit to ground state, nothing but 1st orbit. We don't have 0th orbit. Come on, you can calculate the number of spectral lines. Yes. The number of spectral lines can be given as 5 into 5 minus 1 by 2. So that comes out to be 10, right? Because 5 minus 1 is 4. 2 2 is a 4. So that is 10. Let me show you what those 10 lines are if you want. Let me give you some more clarity on this. Yes, of course. First, second, third, fourth, and fifth are there. Come on. Fifth to first, say fourth to first, third to first, second to first. You get 4 lines in Lyman series. 4. Okay. Now when you go for Balmer, fifth to second, fourth to second, third to second. So in Balmer you get 3 lines. Even this also is important. 4 in Lyman, 3 in Balmer. Let's see how many in Paschen. Okay. 2 in Paschen. And finally, check this out. See, just 1 in bracket. If you want, you can also give the region. Sometimes even the regions are asked. Number of spectral lines formed in a visible region or UV region or near IR region or middle IR region. Of course, we will solve problems, interesting ones later on. But for now, I think it is clear. 4 plus 3 plus 2 plus 1. A total of 10 spectral lines formed when electrons get de-excited from 5th orbit to 1st orbit. Got it? Now let me give you the second one, which of course can be used replacing the first one. First one is a part of the second one. Come on, check this out. So this actually is from any higher energy level to any lower energy level. Any higher to any lower. You know, when I say any lower, it also includes your ground state. So this can be used for anything. Even the first one is included in this. You know, in such a case, the number of spectral lines can be given as n into n plus 1 by 2. But here the condition is n is nothing but n2 minus n1. Higher energy level minus lower energy level. Let me give you an example. Say from 6th orbit to 2nd orbit. Okay. So here n1 of course is always lower. N2 of course is higher. 6. So what is your n here? N is n2 minus n1, nothing but 4. Therefore, the number of spectral lines can be given as what? 4 into 4 plus 1 by 2. So this is nothing but 10 again. Correct? So this way you can calculate the number of spectral lines formed when electronic de-excitation occurs from any higher energy level to any lower energy level. Right? Let me also give you one more relation. Number of a fine line. This is interesting. What do you mean by fine line? Till now, we have discussed only about the spectral line. But you know, once it was found by Sommerfeld that every orbit is made of suborbits. In fact, the concept of suborbits was introduced by Sommerfeld. Now, this is a spectral line. This spectral line, you know, suppose if you consider this as the third orbit. You know, the third orbit will have 3 suborbits. We know that they are 3s, 3p, 3d. I'm just going for the example straight away. And when you go for the second orbit, we know that a second orbit contains 2 suborbits. What are they? 2s, 2p. Now, if you want the number of spectral lines formed when electronic de-excitation occurs from third orbit to second orbit, you know, the number of spectral lines is only 1, because it is possible only when you go from third to second. So spectral lines is just 1. Now let us check the number of fine lines. Now fine lines are due to the suborbits or sublevels in the main level. Now check out, from any higher sublevel to any lower, say from 3s, electron may get de-excited to 2s. 3s to 2s, it may be from 3s to 2p also. So from one of the sublevels of the third orbit to both the sublevels of the second orbit. Got it? Now let us do the same thing in case of 3p also. So come down from 3p to say 2s. From 3p even to 2p also. I'm done. Now when you go for this, come on from 3d to 2s. Similarly from 3d to 2p. These are called fine lines. So how many fine lines are formed? It is 6. So let me give you that the number of fine lines is of course n1 into n2. So in this case n1 is 2 and n2 is 3. Therefore the number of fine lines is 6, because n1 into n2 is 2 into 3, nothing but 6. See, these are the fine lines. Now these fine lines are due to the presence of suborbits. This is the regular spectral line. So when I say number of spectral lines formed when the electronic de-excitation occurs from third orbit to second orbit, say just 1. When I say the number of fine lines, say 6. This is most interesting, right? So this is about how to find the number of spectral lines formed when electronic de-excitation occurs from any higher energy level to ground state, the first case, from any higher energy level to any lower energy level, the second case, but this second one, in fact, includes the first one also. And finally, the third one is calculation of the number of fine lines. This is all about the mathematical part of hydrogen atomic spectrum. Now we are very much ready to solve the problem on hydrogen spectrum.